A very good afternoon to all of you. And as all of you know that we have been going through the course of nanophysics, and mostly in this course we have to learn about the physics that is involved in describing the properties of nanomaterials. And we already have taken care of a good number of videos on the physics of nanomaterials. And as long as the materials are concerned, different materials have different properties. You can have a material made of, say, atoms of type A. You can have a material made of the atoms of type B, and so on. And since the moment we subject these materials to an external, and we call it a disturbance, the material has a response. It responds. Now that response tells us that what are the plausible properties of the particular material. And the simplest example is classifying materials based on conductivity. You can classify materials based on magnetism, the magnetic properties. You can classify materials based on hardness, mechanical strength. You can differentiate materials based on any other physical quantity. So it's the response of the material that makes us realize that what could be the plausible implications of the material. Now, if I take a simple case, assuming that we have solids, and broadly what we can say is that solids can be classified into three categories. You can have based on their electrical properties. You can have solids which are electrically conductive, which you call as conductors. You can have solids that are not conducting at all, even if the potential difference across that solid is extremely large. And you can have solids whose conductivities can be between the conductors and insulators. So classical physics tells us that why some of the materials are conductors and why some other materials are insulators. And we have the laws, the classical laws that are governing the mechanics of the charge that's present in these solids. Are you getting my point?
Yes, sir.
So, even if we move from the classical framework, what we call as drug model, we can explain the properties of these materials using Schrodinger's equation. And we have already discussed in condensed matter physics, we must have talked about the Cronin-Penny model. The model that differentiates a conductor from an insulator, a conductor from a semiconductor. Now, what is the reality? What's the reality of these materials which are called as bulk materials? You have a material made of gold, okay? You have a material made of copper. You have a material made of aluminum. And if you have to describe the properties of these metals, you will assume that the network of these materials is infinite for an electron. Now, what does that mean? That means if I have a bulk material of copper, copper is a good conductor of electricity, is it?
Yes, sir.
Obviously, when you apply the potential difference across, what happens? You say there is flow of current, right? And the flow of current is assigned to the electrons. But the electrons that you are considering in these bulk materials, they never see the boundary. We assume that the electron is moving in an infinite system, where this electron will never see the boundary. And using this argument, we are able to solve the Schrodinger's equation. We are able to do the physics, the quantum physics of these materials, and we are able to classify materials based on whether some materials are conductors, some are semiconductors, and some are insulators. And we have a very famous differentiation that we finally come up in case of solids, and that's called the band theory of solids, where you differentiate a conductor from an insulator merely by measuring the band gap. If the valence band overlaps on the conduction band, you call it a conductor. If the conduction band and valence band, if there is a large separation between these two bands, you call it an insulator. And if there is an intermediate gap of the order of how many electron volts? Of the order of 1 electron volt, you call it a semiconductor. So these are your broader classifications of bulk materials. But here what we have assumed that electron will never see the boundary. It's moving in a constant potential or in a periodic potential of that crystal, but it is never experiencing the surface of that crystal. Now, if I take an example of a cubical box, suppose I have a cubical box. Let us assume that the length of this cubical box is 1 meter. What will be its volume? 1 meter cube. Okay, nothing wrong with the volume. But what will be its total surface area? You will add up the area of each face and you will get the total surface area. Right?
Yes, sir.
Now, if I break this cubical box into 1 lakh boxes, you have a cubical box. I will break this box into how many boxes? 1 lakh cubical boxes. The volume of 1 lakh cubical boxes will be the same as that of the volume of the cube that we chose, isn't it? But what about the surface area? Will it remain same? It will not only change, but it will increase exponentially. So, by miniaturizing the size of your sample, you are increasing the surface area of your sample. You are exposing your sample more to the external circumstances. And you have the same material, 1 meter cube. If you calculate the area of 1 meter cube and you calculate the area of 1 lakh of cubical boxes that you will make out of this, you can calculate it on the paper and you will see that there is a large difference in the surface area. So if there is large difference in the surface area, there must be there must be a total change in terms of the property of this material. Because you are exposing more atoms, you are exposing more molecules to the surroundings. Now, what does it mean? What does it tell us? First, if I think about this cubical box, in this cubical box, if I choose an electron, and this electron is moving in this cubical box, for this electron, the roadmap in this 1 meter cube cubical box is infinite. It will never see the surface. But when you are breaking it, I mean to say, I used the number 1 lakh. If I replace this one number by 1 billion cubical boxes, and 1 billion means 10 to the power of 9. If I make 10 to the power of 9 billion boxes, now think about 1 box. What will be the length of a billionth cubical box in this example? It will be 10 to the power of minus 9 meters. And what is the diameter of an atom? Hey, come on. It's 10 to the power of minus 10. So you are going very, very close to the atomic scale, even though it's not an atomic scale. We have the physics. We have the physics at the atomic scale. We are going very close to that atomic scale. Now imagine an electron in that 1 cubical box. This electron will experience the surface of that cubical box. Right? So, this 1 cubical box that you have got out of a cubical box of whose length was 1 meter, will it behave in the similar way as it was behaving when it was in the bulk form? Will it behave in the same fashion? Now see, if somebody tells you, hey, come on, I have a wire of copper, what will come to your mind at the very first point? You will say copper is a very good conductor of electricity. Now I am taking the same copper, but I am taking its nano-sized part. It is also copper.
Yes, sir.
What it is made up of? It's made up of copper atoms. What would you expect? Will it have the same properties?
Yes, sir. Yes, sir.
Yeah, what nonsense you are saying?
No, sir. It will change.
If you see it in the classical framework, if you see it in the bulk material framework, you will say, come on, copper means copper. Copper means conductor. If I have a nano particle of copper, it will also be a conductor. But that's not what is observed. It does not behave like a conductor. Its properties change. When you take your material from the bulk state to the nano state, the copper no longer remains a good conductor of electricity. There are possibilities now. Copper can become insulator. Copper can become semiconductor. Copper can have a color other than that of the yellow color that it has. So the question arises, why? Why does the properties of the same material, which is a good conductor at the room temperature, why it changes when we take it to the nanoscale? And the answer lies to the argument number one. The argument number one is, the ratio between surface area and volume increases. You are exposing more atoms to the surroundings. And the next important reason, maybe the only important reason, the electron is no longer in an infinite sea. The electron is close to the boundaries of the material. The electron is somehow closely related to a particle in a box situation. The electron does not have continuous energies as in the case of the bulk materials. The electron has discrete energies. That means there is a complete transformation. A thing that is a very good conductor in the bulk form, it may not be a very good conductor at the nanoscale. It might have a property which is different than that of the bulk material. So this is already done in the course. We have already discussed it in our previous classes. Now today we will be talking about some of the important categories of nanomaterials. Now, what does nano mean? It's 10 to the power of minus 9. So, if you will cut 1 meter rod into a billion parts, a billionth part will make 1 nanometer. So, when you are working in the nanoscale, you are working in a scale where electron has discrete energies. And this electron has a resemblance with that of the particle in a box situation. Now what we are doing, we are designing these nanomaterials. We design these nanomaterials. There are two approaches. One is called top-down, another is called bottom-up. So in bottom up, you create the conditions where there is bonding between the atoms and they form the nanomaterials. And in top down case, you break down your bulk material to a very, very small scale. It's called as nanoscale. Now the question is, what is a quantum dot? What is a quantum wire? And what's a quantum well? Now you see, I can tell you that you can have a material which has obviously three axes, X, Y, and Z. In material science, you can do magics. I mean, you have the same material. The same material can behave like a conductor along x-axis. It can behave as an insulator along y-axis. It can behave semiconductor along z-axis. So depending on the way that you have manufactured these materials, the way that you have grown these materials in the laboratory. Now what we have nanostructured materials, but we can classify them into three categories as quantum dots, quantum wires, and quantum wells. So if you look at this slide, for quantum dots, all the three dimensions are 0 dimensions. They are all falling in nanometer range. If you have this kind of situation, you would call it a quantum dot. For quantum wire, only one dimension is in nano range. The other two dimensions are in bulk range. In quantum wells, what you have? You have two-dimensional situation. So this is how you can classify your nanomaterials based on which dimension is in nanoscale. And then you can classify your material as 0D, 1D, and 2D as quantum dots, quantum wires, and quantum wells. Now, look at this problem. First, you had an electron, say this electron's name was A. It was in a bulk material. And for this electron, there is no boundary. There is no boundary. Now, I'm confining this electron at a nanoscale. The properties that it was showing us when it was in the bulk material, they change. Now, this change in the properties of the materials is called as quantum confinement. We call it quantum confinement. I mean, if you will study a nanoscale structure, you will find that there will be a deviation. There will be a deviation in its band gap. And human nanomaterial can be blue shifted. And blue shifted means, you remember that equation E equals h nu. So E is equal to hc by lambda. So corresponding to each lambda, you have a corresponding energy. You will find maybe the band gap will increase if you go to the nanoscale. Maybe the band gap will decrease if you go to the nanoscale. Now this shifting of the property from bulk material to the nanomaterial is called quantum confinement. Because you are confining your electron in a nanoscale range, and certainly the properties of your materials are changed. So when the particle's dimensions, now look at the definition over here. When the particle's dimensions are comparable to the de Broglie wavelength, quantum effects dominate. It was not effective when you had a very infinite network of atoms, but it is when your particle, the nanoparticle, if its dimensions are comparable to the de Broglie wavelength. So in that case, quantum effects dominate, and this is what is called as quantum confinement. Okay, for quantum wells, we have 2D structures confining electrons in one dimension. You are confining your electron, say, along Z, but you are not confining it along X and Y. So along X and Y, your material is behaving as bulk, but along Z, it's not. And you call it what? It's a quantum well. And the examples, gallium arsenide, are these kind of heterostructures you can develop in the form of quantum wells. I'm getting my point. You can use the same material as an insulator, say for example in this direction, a conductor along X and Y. It has applications in lasers and detectors. Now here we have tried to define these things using these diagrams. You can easily see a quantum well, a quantum wire, and a quantum dot. Okay? So you can easily differentiate the three categories of nanomaterials. Obviously, if you have to solve the problem of nanomaterials, you have to solve the Schrödinger's equation. Right? And your problem is an electron in a bound system. It's a bound state. So the problem is exactly same as that of solving the Schrödinger's wave equation on particle in flux. And that leads us to what? Energy separations. Now see, what does it mean, energy separations? Now see, if we think about a conductor, you will say, so there's this much of band gap. In this case, there is this much of band gap, there is this much of band gap. But here, for the same material, you can have different energies. That means you can emit the light of different colors. You can have a blue color, red color, green color, a superposition of these colors. Tunable properties. You are making your material tunable. It can have a range of properties that you can utilize in technology. So for quantum wires, we call them 1D structures, confining electrons in 2 dimensions. You confine them along X and Y. You don't confine them along Z. The same examples. Applications in nanoelectronics. So this was the diagram that I showed you. Again, the Schrödinger's equation plays a very important role, and once you solve the Schrödinger's equation, you come up with an equation of energy. And once you come up with an equation of energy, you can calculate the very important property of solids, what's called as density of states. You will see these lectures. They are already uploaded. Okay? So you can see that how the density of structures, the density of states shows a different category, a different nature at nanoscale. So for quantum dots, what you have? 0D nanostructures confining electrons in all the three dimensions. Electron is confined along x. That means x is in a nanometer range, y is in a nanometer range, and z is in nanometer range. So you call it a quantum dot. And examples, CDSE quantum dots. It has applications in light emitting diodes, biomedical imaging. See, this quantum dot is a very, very strong tool in the modern medical science. It may replace the treatment of cancer using radiation. We have a way of treating cancers. What is that way? You can have a chemotherapy or you can have a radiation therapy. And all of us understand that the radiation therapy, it does not kill only the cancerous cells, it kills the good cells also. So the probability of getting the cure done, this probability decreases. And the patient has to suffer a lot. It's very painful. But this radiation therapy that we use to treat the cancers, it can be replaced by these quantum dots. These quantum dots may not only image the tumor. See, what is happening in medical science? If somebody has a tumor, the first you have to photograph it, right? And for photography, again, you are using the radiation. And once you photograph it, now you will try to target it. You will try to hit it with the nuclear radiations. But here, we can do both the things. We can send these quantum dots to the point where there is a tumor. And these quantum dots will act as nanorobots. They will just go to the points. They will just go to these points of distraction, these points where there's the growth of unwanted cells. They will map them. They will photograph them. And then these quantum dots, these nanorobots, can be sent to the same tumor by transporting the medicine to that tumor. Or you can have a barrage of robots who can sense only cancerous cells. And they will go and they will mechanically eat the cancerous cells. And they will not hurt the normal cells. Now, this technology is not real till now, but science goes with these domains of arguments. There is a possibility. In fact, some of the things have already happened. The world is running. The tumors might become plausible in terms of treatments. You can treat them in a very, very easiest way, rather than that of complicating and creating a painful situation for the patient. So here, that's what I was talking about, that these quantum dots may not only be used for biomedical imaging, they may be used to take the medicine. They may be used to treat those abnormal cells in our bodies. So now these quantum dots, they behave like artificial atoms. They are not actually atoms. There's a bunch of atoms in these nanomaterials. They have discrete energy levels. And now you know why they have discrete energy levels. Because the electrons are confined in a very, very short scale, and at this scale the quantum mechanical effects are dominant, and you are confining your wave function in all dimensions. You can compare them 1D, 2D, 3D in terms of the dimensions, as we have discussed about that. And in terms of the quantum confinement changes, the energy spectra and the density of states. Because once you have energy E equals m square pi square h cross square by 2ml square, you can calculate the density of states as dm by de. So they have applications in semiconductor lasers, nanoscale transistors for quantum wires, and solar cells and displays in case of quantum dots. Quantum device, they are in process. People are trying to build the quantum computers. Americans are building it at IBM, and Chinese people are also building the quantum computers. And they will have a role in communication, sensing, the quantum dot qubits, the quantum bits. In a quantum computer, you don't have zeros and ones, you have quantum bits here. Your quantum computer works on quantum bits. And your quantum bits can be state 1, state 2, or the superposition of these states. And certainly they can be integrated into photonic systems. So to conclude this, what we have, you can have tunable properties of your materials. You can tune the properties of your materials at nanoscale. Not only electrical properties, but also optical properties, magnetic properties, mechanical strength properties, and certainly these nanomaterials are enabling us to new technologies in quantum science. So this was an introduction to these classes of nanomaterials, which we call as quantum dots, quantum wells, and quantum wires. Any questions? You can ask me.
No, sir.
Come on. Close it.